March 18th, 1943, Fort Benning, Georgia. The Willys MB Jeep tumbled from the C-47 transport plane, its dark green silhouette momentarily suspended against the clear sky before gravity took hold. 500 feet below, a small crowd of officers and engineers watched with professional interest as the vehicle plummeted toward the drop zone. Parachutes deployed with a crack, slowing the descent but still allowing the 2,000-pound vehicle to slam into the Georgia clay with bone-jarring force. When the dust settled, engineers approached cautiously, clipboards in hand, expecting to find a twisted wreck of metal. Instead, they discovered something remarkable. Despite the violence of its landing, the Jeep's frame remained intact. Its wheels were splayed at unnatural angles, the windshield shattered, but the fundamental structure, that seemingly crude, overbuilt frame, had survived. One engineer turned to the others with undisguised astonishment. It shouldn't have held together. No vehicle frame should withstand that kind of impact, but it had. And the story behind that improbable survival began 2 years earlier, with a welder at the Willys Overland plant in Toledo, Ohio, whose unconventional approach to frame design would ultimately save countless Allied lives. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. July 10th, 1941. The Willys Overland factory floor buzzed with activity as workers rushed to fulfill the Army's massive order for the newly approved MB model, what soldiers were already calling Jeeps. Among them stood Harold. Mitchell, a 36-year-old welder whose 20 years of experience in automotive manufacturing had taught him that conventional wisdom often deserved questioning. Mitchell had spent the previous decade working at various automotive plants throughout the Midwest, including stints at Ford, Packard, and finally Willys Overland. What distinguished him from many of his colleagues was his willingness to challenge established practices. When Willys Overland won the coveted Army contract to mass-produce what would become the iconic Willys MB Jeep, Mitchell found himself assigned to the frame welding station. The original frame specifications called for standard automotive design principles, lightweight yet strong enough to handle the vehicle's intended purpose as a reconnaissance and light utility vehicle. But Mitchell had spent the previous evening reading newspaper accounts of early Jeeps being tested in field conditions. What caught his attention wasn't the glowing praise from officers, but the casual mentions of abuse these vehicles endured. Drivers were pushing them through mud holes that swallowed half the vehicle. They were driving them up near vertical slopes. They were loading them beyond their rated capacity. And somewhere in that newspaper account, Mitchell read something that wouldn't leave his mind. Speculation that these vehicles might eventually be dropped from aircraft to support airborne operations. The next morning, Mitchell approached his supervisor with concerns about the frame specifications. These frames won't hold up to what they're going to put these vehicles through, he argued. Look at how they're using them already, and that's just in training. What's going to happen in actual combat? His supervisor dismissed the concerns. We build to specification, Mitchell. The Army engineers know what they're doing. But Mitchell remained troubled. He understood that wartime reality rarely aligned with peacetime engineering assumptions. During his lunch break, he sketched an alternative frame design on the back of his time card. Heavier, with additional reinforcement at key stress points, and crucially, a different welding pattern that distributed impact forces across the entire structure rather than concentrating them at the joints. That afternoon, without explicit authorization, Mitchell began subtly modifying the welding pattern on the frames passing through his station. He didn't alter the basic dimensions or materials, changes that would have been immediately noticed, but he added reinforcement welds at critical juncture points and modified the welding pattern to create what engineers would later revise, call a unified stress distribution system. It was, by conventional automotive standards, over-engineered and unnecessarily robust. Mitchell knew his modifications added approximately 40 pounds to each vehicle, weight that efficiency-minded engineers would have eliminated. But he wasn't designing for efficiency, he was designing for survival. For several weeks, Mitchell's modifications went unnoticed amid the frantic pace of wartime production. Willys Overland was under enormous pressure to meet delivery quotas, and quality control focused primarily on critical components and final assembly, rather than examining welding patterns on frames. This changed in early August when a young engineer named Robert Thompson conducted a random weight check on completed vehicles and discovered that frames from Mitchell's shift consistently weighed more than those from other shifts. Thompson traced the discrepancy to Mitchell's station and confronted him about the unauthorized modifications. Mitchell faced a difficult choice: admit to violating production protocols or defend his reasoning. He chose the latter. "I've been reading about how these vehicles are being used," he explained to Thompson. "They're being driven through hell already, and that's just in training. In combat, they'll face worse. Standard frames won't handle it." Thompson was skeptical but intrigued enough to examine Mitchell's modifications more closely. What he found surprised him. The additional welds and reinforced stress points were professionally executed and reflected a sophisticated understanding of how force would be distributed through the frame under extreme conditions. "You realize this adds unnecessary weight," Thompson pointed out. "Unnecessary in normal conditions," Mitchell countered. "But these won't be used in normal conditions." Thompson might have reported the modifications and had Mitchell disciplined or reassigned. Instead, he made a decision that would prove consequential for the war effort. "Keep doing what you're doing," he told Mitchell. "I'll run some tests on your frames versus the standard design. If your approach proves superior, we'll consider formalizing the changes." This quiet agreement between a shop floor welder and a junior engineer initiated what would become one of the most significant unofficial modifications to Allied equipment during World War II. Thompson began subjecting both standard frames and Mitchell's modified versions to increasingly severe stress tests, documenting the results meticulously. September, the evidence was compelling. Mitchell's frames consistently withstood stress levels that damaged or deformed standard frames. Under extreme torsional stress, the twisting force that occurs when wheels encounter dramatically different terrain, the standard frames showed stress fractures at the weld points. Mitchell's frames distributed the force more evenly, preventing catastrophic failure. Most significantly, in drop tests designed to simulate the vehicle hitting a shell crater or falling off an embankment, Mitchell's frames survived impacts that collapsed standard frames. Thompson took his findings to the chief engineer at Willys Overland, presenting both the test results and Mitchell's reasoning. The chief engineer initially rejected the modifications, citing the Army's specifications and the additional weight. "We're contracted to build to these specs," he reminded Thompson. "If the Army wants changes, they'll send revised specifications." Thompson persisted, arguing that the field performance would justify the modification. "Soldiers' lives might depend on these vehicles holding together under conditions we can't even anticipate," he argued. "Mitchell's design gives them a better chance." The chief engineer remained unmoved. "We follow specifications," he repeated. "That's how manufacturing works, especially in wartime production." That might have been the end of Mitchell's modification, if not for an unexpected development. In mid-September, the Willys Overland plant received a visit from Colonel William Lee, who would later become known as the Father of the Airborne for his role in developing American airborne forces. Lee was visiting various manufacturing facilities to evaluate equipment that might be suitable for airborne operations. During his tour of the Willys plant, Thompson seized the opportunity to show Lee the test results, comparing standard frames with Mitchell's modified design. Lee, a pragmatic officer with extensive field experience, immediately grasped the implications. "You're telling me this modified frame can withstand significantly more abuse?" Lee asked. "Yes, sir," Thompson confirmed. "Especially impact forces similar to what might occur during airborne delivery." Lee's interest was piqued. The Army was already exploring methods for delivering vehicles and heavy equipment to airborne troops, a capability that would prove crucial for sustaining operations behind enemy lines. "I want to see these test results," Lee said, "and I want to meet this welder." The meeting between Colonel Lee and Harold Mitchell was brief but consequential. Mitchell explained his reasoning simply. "I built the frame I'd want to be riding in if someone was shooting at me." Lee arranged for several Jeeps with Mitchell's modified frames to be sent to Fort Benning for testing with the nascent airborne divisions. The results confirmed Thompson's findings. The modified frames withstood abuse that damaged or destroyed standard frames. More importantly, when early experiments with air-dropping vehicles began, Jeeps with Mitchell's frames survived drops that would have destroyed conventionally framed vehicles. By late 1941, without any formal revision to specifications, Willys Overland had quietly adopted Mitchell's frame modifications as standard practice. The company never officially acknowledged the change, likely to avoid addressing why they had deviated from Army specifications. The impact of Mitchell's unauthorized modification became apparent when the first Jeeps reached combat zones in North Africa in early 1942. Field reports began filtering back to the War Department, describing Jeeps surviving conditions that should have rendered them inoperable. One report from the 1st Infantry Division detailed a Jeep that had driven over a German anti-tank mine. The explosion had destroyed the front axle and engine but left the frame intact, allowing the crew to survive. Another report from Tunisia described a Jeep that had fallen 30 feet into a ravine during a night operation. Despite the severity of the crash, the vehicle's frame remained intact, and the vehicle was recovered and returned to service after repairs. What made these survival stories remarkable wasn't just that the vehicles had endured extreme conditions, it was that they had done so consistently. Military equipment has always faced abuse beyond its design parameters, but typically with catastrophic results. Mitchell's frames were proving different, surviving conditions that should have destroyed them entirely. The practical implications for the war effort were significant. Vehicles that survived severe accidents could often be repaired rather than replaced, reducing the logistical burden of shipping replacement vehicles to forward combat areas. More importantly, crews who might have been killed or seriously injured in vehicles with standard frames often walked away from accidents involving Mitchell's reinforced frames. By early 1943, the Army had accumulated enough field experience with the Willys MB to recognize that it possessed extraordinary durability. What they didn't know was that this durability stemmed largely from an unauthorized modification made by a welder who had never been to college, never held an engineering title, and never received formal recognition for his contribution. When the Army contracted for a second production source for the Jeep, awarding a contract to Ford to produce the nearly identical GPW model, they provided detailed specifications that included, without explicitly identifying them as such, Mitchell's frame modifications. Ford engineers, examining the Willys MB as their production model, noted the seemingly excessive frame reinforcement, but dutifully reproduced it in their version. The true test of Mitchell's design came in the summer of 1943, when the Army Air Forces began serious experiments with air-dropping vehicles to support airborne operations. The concept was audacious, delivering fully assembled Jeeps and other equipment by parachute, allowing them to be operational immediately upon landing. The technical challenges were enormous. A 2,000-pound vehicle falling from aircraft altitude, even when slowed by parachutes, still hit the ground with tremendous force. Early tests with standard military vehicles proved disastrous, with frames buckling on impact regardless of how many parachutes were used or how carefully the drops were executed. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. When Jeeps entered the airdrop testing program, military engineers expected similar results. Instead, they witnessed something remarkable. While the Jeeps certainly sustained damage, broken axles, damaged wheels, shattered windshields, their frames largely maintained structural integrity, allowing the vehicles to be quickly repaired and put into service. What the engineers didn't realize was that they were witnessing the real-world validation of Harold Mitchell's frame design philosophy. The unnecessarily robust frame that added 40 pounds to each vehicle was proving its worth under the most extreme conditions imaginable. Colonel Lee, who had met Mitchell and championed his modification, recognized the significance immediately. "This capability changes everything for airborne operations," he noted in a report to Army Ground Forces Command. "The ability to deliver operational vehicles to airborne troops dramatically extends their range and combat effectiveness." By the time the Allies were planning the Normandy invasion, the airdropping of Jeeps had moved from experimental concept to operational capability. Plans were developed to deliver Jeeps by parachute to support airborne divisions dropped behind German lines. At the Willys Overland plant in Toledo, production continued at a frantic pace, with thousands of Jeeps rolling off the assembly line monthly. Harold Mitchell had been promoted to shop foreman, overseeing the frame welding section and ensuring that every frame incorporated his modifications. He never sought recognition for his contribution, viewing it simply as doing his job properly. When occasional visitors from the War Department toured the facility, none recognized that a critical design element that was saving lives in combat had originated not in an engineering office, but on the factory floor from a welder who had trusted his instincts over official specifications. In March 1944, Mitchell received a letter that he initially mistook for a draft notice. Opening it with apprehension, he instead found a brief note from an army major serving with the 1st Infantry Division in Italy. The letter was simple. "Mr. Mitchell, I don't know if you had anything to do with the frame on my Jeep, but whoever built it saved my life and the lives of my men when we drove over a mine outside Anzio. The vehicle was destroyed, but the frame held. We all walked away. Thank you." Mitchell never discovered how the major had learned his name or role in the Jeep's production, but he kept the letter in his wallet for the remainder of the war as his only tangible connection to the impact of his work. As the Allied invasion of Nazi-occupied Europe approached, the significance of Mitchell's frame modification became increasingly apparent to those involved in airborne planning. The 82nd and 101st Airborne Divisions would be dropped behind enemy lines in Normandy the night before the beach landings. Their mission was to secure key crossroads and bridges, preventing German reinforcements from reaching the beaches. To accomplish this, they would need mobility beyond what foot soldiers could provide. They would need vehicles, specifically Jeeps, delivered by air alongside the paratroopers. The logistics were daunting. Loaded C-47 aircraft would drop paratroopers first, then return to make additional runs, dropping equipment bundles and vehicles. The Jeeps would be rigged with multiple parachutes and dropped from low altitude, hopefully landing in designated drop zones where paratroopers could quickly recover them. The success of this operation depended entirely on the Jeeps surviving the drop with minimal damage, something that would have been impossible without Mitchell's reinforced frame design. As D-Day approached, neither Mitchell nor anyone at Willys Overland knew that their vehicles were about to play a crucial role in the largest airborne operation in military history. June 5, 1944. The airfield in southern England hummed with nervous energy as paratroopers of the 101st Airborne Division prepared for history's largest airborne assault. Operation Neptune, the airborne component of the Normandy invasion, would commence in less than 24 hours. Among the invasion force, a specialized detachment focused on a unique task, recovering and assembling the Jeeps that would be airdropped to support the paratroopers after they landed. Staff Sergeant James Erickson checked his equipment one final time, mentally rehearsing the assembly sequence they had practiced countless times. His 6-man team was responsible for locating and assembling 3 airdropped Jeeps within the first 4 hours after landing. "Nervous?" asked Lieutenant Frank Hargrove, approaching with clipboard in hand. Erickson shook his head. "Not about the assembly, sir. We can put those Jeeps together blindfolded. It's the finding them in the dark while being shot at part that concerns me." Hargrove nodded, understanding the challenge. The air-dropped Jeeps would land in containers holding the disassembled vehicle frame, engine block, transmission, axles, wheels, all separated to survive the impact. Ericsson's team would have to locate these containers, often scattered across hostile territory, then assemble the vehicles under combat conditions. "We've had good results in practice drops," Hargrove reminded him. 87% successful recovery and assembly. Ericsson nodded. The statistics were impressive, a testament to both the ruggedness of the Jeep's design and the skill of the assembly teams. What neither man mentioned was the critical element that made those statistics possible, the specially designed frames that could withstand the impact of parachute drops. Without those frames, the entire concept would have been impossible. "Just remember," Hargrove added, "those Jeeps are as important as ammunition. The entire airborne operation depends on mobility after landing." As darkness fell across the English countryside, the paratroopers made final preparations. Equipment checks, weapons inspections, last letters home. The invasion years in, planning would commence with their midnight drop behind enemy lines. Ericsson thought about the Jeeps they would assemble tomorrow, machines built by workers in factories thousands of miles away. He wondered if those factory workers understood how crucial their workmanship would prove in the coming hours. In Toledo, Ohio, Harold Mitchell worked the night shift at the Willys Overland factory, supervising the frame welding section. He had no knowledge of the impending invasion, no awareness that Jeeps with his reinforced frames were already loaded into aircraft for the most significant military operation of the war. Like millions of American workers, Mitchell performed his duties with quiet determination, his only connection to the front lines being occasional letters from servicemen and War Department reports about equipment performance. The relationship between the factory floor and the battlefield remained abstract, the impact of production decisions largely invisible to those who made them. As Mitchell inspected a newly completed frame, applying his practiced eye to the weld patterns, a young welder named Thomas Jenkins approached. "Mr. Mitchell, I've been meaning to ask, why do we add those additional reinforcement welds? They're not in the original blueprints." Mitchell paused, considering how to explain the modification that had become standard practice without official acknowledgement. "Because soldiers' lives depend on these frames holding together," he said simply. "And in the field, these Jeeps face conditions no engineer could anticipate." Jenkins nodded, satisfied with the explanation, and returned to his station. Mitchell watched him go, wondering if the young man truly understood. How could anyone who hadn't seen combat grasp what these vehicles would endure? In the early hours of June 6, 1944, C-47 aircraft crossed the English Channel toward Normandy, carrying the vanguard of the Allied invasion force. Among the paratroopers of the 101st and 82nd Airborne Divisions were the vehicle assembly teams, including Sergeant Ericsson's unit. Their drop would be followed hours later by the air delivery of their Jeeps, crucial for providing mobility to officers, setting up command posts, evacuating wounded, and moving heavy equipment like mortars and machine guns. The parachute drop itself proved chaotic. Strong winds scattered paratroopers across the Normandy countryside, miles from designated landing zones. In the darkness, amid sporadic enemy fire, disoriented soldiers struggled to regroup and locate their objectives. Ericsson found himself separated from most of his team, with only Private Williams landing nearby. By dawn, they had located one other team member and received word that their Jeep containers would be dropped at 0800 hours in a field near the small village of Sainte-Mère-Église. Provided Allied aircraft could locate the correct drop zone in the confusion of battle. At the appointed hour, the drone of aircraft engines drew their attention skyward. C-47 transports appeared, flying dangerously low to ensure accurate delivery. From the aircraft came their precious cargo, massive containers suspended beneath bloom-sized parachutes. The containers hit the ground with bone-jarring force, the sound of impact audible even over the distant rumble of naval gunfire from the beaches. Ericsson and his partial team raced to the nearest container, already calculating how 3 men would manage an assembly task designed for 6. Opening the container revealed its contents a disassembled Willys MB, its components secured in custom cradles. The frame Mitchell's reinforced design had survived the drop intact despite the violence of the landing. This was the crucial first victory. Without a solid frame, assembly would be impossible. The team began their work under intermittent sniper fire, using the container itself as partial cover. The assembly sequence they had practiced countless times in England now unfolded under the pressure of combat. Frame first, then axles, engine block, transmission, wheels, body components. 3 hours later, sweating despite the cool morning, Ericsson turned the ignition key. The engine caught immediately, its distinctive rumble a testament to both American manufacturing and the team's assembly skill. Within minutes, the Jeep carried its first cargo, a wounded paratrooper who needed evacuation to an aid station. By nightfall, the vehicle had transported officers to 5 different command posts, delivered ammunition to an isolated platoon, and evacuated 8 wounded men. A single vehicle had potentially saved dozens of lives while dramatically enhancing the unit's combat effectiveness. What Ericsson couldn't know was that his experience was being replicated across Normandy. Of the 37 Jeeps airdropped to support the airborne divisions on D-Day, 29 were successfully recovered and assembled, a 78% success rate under combat conditions. This remarkable achievement depended entirely on frames capable of surviving drops that would have destroyed conventional vehicles. Harold Mitchell's unauthorized modification, born from practical experience rather than engineering theory, had become an essential element of the largest military operation in history. As the Normandy campaign progressed, the durability of the Willys MB Jeep under extreme conditions became legendary among Allied forces. Vehicles survived artillery near misses that should have destroyed them completely. They forded streams that threatened to submerge them entirely. They navigated bomb craters and rubble-strewn streets that would have stopped conventional vehicles. Behind this performance lay Mitchell's reinforced frame, the foundation that made everything else possible. In August 1944, as Allied forces liberated Paris and drove toward Germany, the Army Service Forces commissioned a comprehensive study of equipment performance during the Normandy campaign. Technical experts interviewed frontline units about their experiences, collecting data to improve future designs. A major finding emerged from these interviews: the extraordinary durability of the Jeep frame compared to other military vehicles. Photographs documented Jeeps with bodywork shredded by shrapnel but frames intact, allowing field repairs rather than complete replacement. One photograph particularly impressed the evaluation team. It showed a Jeep that had been caught in a German artillery barrage outside Carentan. The explosion had torn away the hood, fenders, and windshield. The engine had shifted in its mounts, and both front wheels splayed at unnatural angles. Yet the frame remained structurally sound, allowing the vehicle to be towed to a maintenance unit, repaired, and returned to service within 48 hours. The accompanying report noted, "The structural integrity of the Willys MB frame under extreme impact exceeds design specifications by approximately 300%. This unexpected performance margin has proven crucial to field repairability." What the report didn't mention, because the authors didn't know, was that this unexpected performance margin stemmed from Harold Mitchell's welding modifications. The Army engineers assumed the frame's durability represented intentional over-engineering by Willys Overland. They never suspected that a factory welder had quietly modified the design based on his own judgment about combat conditions. The disconnect between frontline reality and production specifications, bridged by Mitchell's practical intervention, remained invisible to those studying the Jeep's performance. As the European campaign accelerated following the breakout from Normandy, the Allies faced a new logistical challenge, keeping pace with rapidly advancing forces. German retreats often involved destroyed bridges and cratering roads, creating obstacles that slowed conventional military vehicles. The Jeep's exceptional frame strength again proved decisive, allowing it to navigate terrain that would have damaged or destroyed less robust vehicles. Combat engineers developed techniques for rapid reinforcement of damaged bridges, specifically sized for jeeps, enabling reconnaissance and communication when heavier vehicles couldn't pass. In September 1944, the Allies launched Operation Market Garden, the ambitious airborne assault into the Netherlands. Again, airdropped jeeps played a crucial role, with improved container designs based on Normandy experience. The 82nd Airborne Division reported 92% successful recovery and assembly of airdropped jeeps, a dramatic improvement over D-Day. This success directly influenced field mobility during the operation's critical early hours, allowing commanders to respond rapidly to unexpected German resistance. By late 1944, the cumulative impact of Mitchell's frame modification had become measurable in statistical terms, though few recognized the connection. Army ordnance records from the European theatre showed that jeeps required complete frame replacement at 1/7 the rate of other military vehicles exposed to similar conditions. This translated directly to increased vehicle availability, machines remaining in service rather than awaiting replacement parts, which in turn affected combat effectiveness. Field maintenance units reported that jeeps with severely damaged bodies often remained drivable, allowing emergency evacuations and critical supply deliveries, even after suffering damage that would have immobilized other vehicles. December 1944 brought the ultimate test of the jeep's durability during the Battle of the Bulge. As German forces launched their surprise offensive through the Ardennes forest, American units found themselves fighting in blizzard conditions over frozen, mountainous terrain. Temperatures plunged below zero, roads turned to ice, and snowdrifts reached axle height on vehicles. Under these conditions, the jeep's frame strength again proved decisive. The torsional forces created by driving through deep snow or over ice-covered obstacles would have twisted conventional frames beyond usability. Mitchell's reinforced design distributed these stresses, allowing the vehicles to maintain structural integrity despite conditions that immobilized many heavier vehicles. A particularly notable incident occurred during the siege of Bastogne, where the 101st Airborne Division found itself surrounded by German forces. Medical supplies ran critically low, with wounded soldiers dying for lack of plasma, morphine, and antibiotics. When weather cleared briefly on December 23rd, allowing C-47 aircraft to attempt supply drops, the packages landed across a wide area due to high winds and pilot caution about German anti-aircraft fire. Jeeps from the division's motor pool navigated nearly impassable terrain to retrieve these supplies, their frames withstanding impacts that buckled body panels but left the vehicles operational. By the time Allied forces crossed the Rhine into Germany in March 1945, the Willys MB Jeep had earned a reputation as possibly the most reliable and durable vehicle in military history. German prisoners expressed particular admiration for the Jeep's frame strength, with captured Wehrmacht mechanics noting that German equivalent vehicles couldn't withstand comparable abuse. This assessment echoed through technical intelligence reports, with German engineering officers acknowledging that the Jeep's frame design represented an approach to durability that German automotive philosophy had overlooked, emphasizing practical survivability over theoretical efficiency. In Toledo, Ohio, Harold Mitchell continued supervising frame production, unaware of how his modification had transformed the vehicle's combat performance. Wartime security meant that specific field reports rarely reached the factory floor in unfiltered form. Mitchell knew only that the Jeeps were performing well and that production continued at maximum capacity. The disconnect between his daily work and its battlefield impact remained unbridged until April 1945, when an Army colonel visited the Willys Overland plant as part of a manufacturing efficiency study. Colonel Robert Harrison had commanded a mechanized cavalry unit during the Normandy campaign and had personal experience with the Jeep's extraordinary durability. During his factory tour, he noticed the reinforcement welds that distinguished Mitchell's frames and asked about their purpose. When the tour guide, a junior engineer, explained that these were standard production features, Harrison shook his head. "I've examined captured German vehicles," he said. "None have frame reinforcement like this. It's what makes your Jeep survive when everything else fails." The engineer, unfamiliar with the modification's history, merely nodded, but a plant manager who had been with the company since before Mitchell's intervention recognized the significance of the colonel's observation. After the tour concluded, the manager approached Mitchell on the factory floor. "That army colonel was just singing the praises of your frame modification," he said quietly. "Apparently, it's been making quite a difference overseas." Mitchell nodded, accepting this rare acknowledgement with characteristic reserve. He had never sought recognition for his initiative, viewing it simply as doing his job properly. Still, confirmation that his judgment had been correct, that the additional welds and reinforcements had actually mattered in combat, provided quiet satisfaction. "Just built them the way they needed to be built," he replied, then returned to supervising his welding team. As the European War neared its conclusion in May 1945, a more complete understanding of the Jeep's impact began emerging through systematic army evaluation. Beyond its operational versatility, the vehicle's exceptional durability had transformed logistical calculations. Jeeps remained in service 3 times longer than anticipated between major overhauls, required 1/5 the spare parts of comparable vehicles, and could be repaired in forward maintenance facilities, rather than evacuated to rear echelon workshops. These factors collectively meant that fewer replacement vehicles needed shipping to the combat zone, freeing cargo space for ammunition, rations, and other critical supplies. When Germany surrendered on May 8, 1945, the true magnitude of the Jeep's contribution became clearer still. Of the approximately 45,000 Willys MBs and Ford GPWs shipped to the European theatre, over 38,000 remained operational at wars, and an 84% availability rate that exceeded every other vehicle type by substantial margins. Post-war technical analysis identified the frame's extraordinary durability as the primary factor in this longevity. Vehicles with damaged engines, transmissions, or body components could be repaired in field conditions, but frame failures typically rendered vehicles unsalvageable. The rarity of such failures in Jeeps directly attributable to Mitchell's modification had proven decisive to field sustainability. The Pacific Theatre provided an even more dramatic demonstration of the Jeep's durability under extreme conditions. On islands like Guadalcanal, New Guinea, and Okinawa, Jeeps operated in environments that destroyed conventional vehicles within weeks. Saltwater corrosion, tropical humidity, volcanic soil, and monsoon rains. Technical reports from Marine Corps maintenance units noted that while engines and electrical systems required frequent service in the conditions, Jeep frames rarely failed despite extreme abuse. The correlation between Mitchell's reinforcement pattern and this performance remained unrecognized, but the practical benefit was unmistakable. Marines maintained mobility in terrain that would have otherwise required everything moving on foot. As the war concluded in August 1945, the legacy of Harold Mitchell's reckless frame modification extended beyond military applications. The lessons of designing for extreme durability, rather than theoretical efficiency, influenced post-war automotive philosophy, particularly in vehicles intended for developing regions with limited infrastructure. The Land Rover, developed in 1948, incorporated frame design principles directly influenced by analysis of the Willys MB. Toyota's early Land Cruiser models similarly reflected lessons learned from studying captured Jeeps during the occupation of Japan. The philosophical approach building to survive abuse, rather than meet minimum requirements, transformed how utilitarian vehicles were engineered worldwide. Harold Mitchell himself never received formal recognition for his contribution. He remained at Willys Overland until 1952, when he retired due to health issues related to decades of welding work. His modification had been so thoroughly incorporated into production that institutional memory of its origins faded. Engineering documents listed the reinforced frame as standard design, with no acknowledgement of its evolutionary development. Mitchell took quiet satisfaction in seeing returned war surplus Jeeps still operating on American farms and work sites, their frames intact despite years of abuse that would have collapsed conventional vehicles. The true impact of his initiative became apparent only decades later, when military historians began systematic interviews with World War II veterans. A recurring theme emerged from these accounts: the extraordinary survivability of Jeeps in situations that should have destroyed them completely. Veterans described vehicles riddled with bullet holes still functioning, Jeeps thrown into the air by nearby explosions, landing upright and drivable, machines that rolled down mountainsides, yet remained operational after basic repairs. Behind each of these survival stories stood Mitchell's reinforced frame, providing the structural integrity that kept everything else together. In 1979, the U.S. Army Transportation Museum assembled an exhibit on the Jeep's development and combat role. During research for this exhibit, curators discovered the original engineering change orders that had quietly incorporated Mitchell's welding modifications into official specifications. Further investigation revealed that these changes had occurred without formal testing or approval, an extraordinary deviation from military procurement procedures. The museum staff located Mitchell, then 84, and living in retirement, in Florida, and conducted an extended interview about his role in modifying the frame design. "I just built them the way I thought they needed to be built," Mitchell explained, echoing his response from decades earlier. The Army would be using these vehicles in conditions no one could really anticipate. Better to make them too strong than not strong enough. When shown photographs of heavily damaged Jeeps that had remained operational due to intact frames, Mitchell nodded with recognition. "That's exactly what I was trying to prevent: catastrophic failure. You can replace an axle or an engine, but once the frame goes, you've lost the whole vehicle." Perhaps the most poignant testimony came from a D-Day veteran who had served with the vehicle recovery team of the 82nd Airborne Division. In a letter to the Transportation Museum, he wrote, "During the first week after the invasion, we recovered a Jeep that had taken a direct hit from a German 28mm anti-tank gun. The round had passed through the engine block and exit the rear of the vehicle. By all rights, that Jeep should have been scrap metal. But the frame held together. We towed it back, dropped in a replacement engine from a salvage vehicle, and had it running again in 18 hours. That same Jeep carried our battalion commander all the way to the German border. Whoever designed that frame saved countless lives by keeping our vehicles running when we needed them most." The irony remains that Mitchell's critical contribution, born from practical experience rather than engineering, theory nearly didn't happen at all. Had he followed specifications exactly, had he not trusted his judgment over official requirements, thousands of Jeeps might have failed under combat conditions. The cascading consequences for operations dependent on their mobility would have been incalculable. D-Day paratroopers might have lacked transportation after landing. Wounded soldiers might have died awaiting evacuation. Supply lines might have broken during critical advances. The margin between success and failure in war often rests on such seemingly minor technical details: a few additional welds on a vehicle frame, added by a worker who understood that combat reality would exceed peacetime expectations. The legacy of Harold Mitchell's modification extends beyond the mechanical into the philosophical. His approach, building beyond minimum requirements to survive unpredictable conditions, represents a mindset that values human lives over theoretical efficiency. In an age increasingly dominated by optimization algorithms and minimum viable products, Mitchell's lesson remains relevant. Sometimes apparent waste in design, the extra material, the redundant supports, the seemingly unnecessary reinforcement proves essential when systems face conditions beyond their expected parameters. The 40 additional pounds that Mitchell's modification added to each Jeep frame represented insurance against catastrophic failure, a weight penalty that saved countless lives. In the final analysis, Mitchell's story exemplifies how victory in World War II depended not just on grand strategy or battlefield heroism, but on countless small decisions made by ordinary individuals throughout the Allied war effort. A welder in Ohio, modifying frames beyond specification. A factory engineer who allowed the modification rather than reporting it. A forward maintenance team improvising repairs under fire. Each represented the practical problem-solving that characterized American industrial, might the willingness to adapt, improve, and overcome obstacles through initiative, rather than rigid adherence to procedure. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.